Welcome everyone to this webinar, Elevate Your eCognition Skills. Today we're going to talk about how to use high resolution imagery and Lidar products for object-based image analysis. Who is who? You're going to hear three people talk today. Myself, I'm Matthias Staengel, a Senior Support and Consultant Engineer for Trimble. Then we have Wang, also Support and Consultant Engineer for Trimble. And then the most important person today is Jonathan Mikolin from Penn State University. He's going to present his project, and I think it's going to be very interesting to see what he has done with eCognition. Let's see the agenda. First of all, this webinar is recorded, so if you have to jump out earlier, you're going to find it online in, let's say, next week. You are all muted, so if you want to ask questions, please use the questions tab. We're going to answer all the questions at the end in the questions and answers section, depending on how much time we have. And yeah, please give us also feedback if the audio is bad or you do not see the screen. Just let us know and we try to fix it. That's the agenda. I'm first going to briefly introduce eCognition. Just one slide. I mean, every one of you is probably an eCognition user or has heard of eCognition. Second part is then Jonathan's presentation, then a Q&A session at the end, and I'm going to have a slide on resources. So if you're interested to use eCognition, where you can go and where you can get free material. Okay, first of all, eCognition. So what is eCognition? It's a tool for automated feature extraction, and the idea is to transform data into information. And yeah, you can do change detection, object detection, information extraction, all that stuff. And I would say the main three unique features of eCognition is OBIA, which stands for object-based image analysis, then data fusion and method fusion. Let's start with OBIA, so object-based image analysis. That means we're not looking at solely at single pixels. We are creating image objects, and then you can address the color, shape, texture, and size of those objects. So you get additional statistics, and you also can address the context and relationships of objects. One example would be you have water, right? And for example, a lake and a river, spectrally, they look the same, but you're going to get elongated objects for the river, and you can address that information in eCognition. And context would be, let's say you want to detect boats or ships in the ocean. If you classify water and then you have those leftover objects that are 100% surrounded by water, those are probably ships or islands, depending on their size, right? So, and that can be done in eCognition. Second point here, data fusion. Yeah, you can load raster images. It can be one single layer. It can be hyperspectral. It doesn't matter, any spatial resolution. Vectors, so points, lines, and polygons, and then point clouds, right? Also doesn't matter which sensor you've used, a Lidar sensor or mobile mapping or terrestrial sensors. It only has to be in LAS or LAC format, and then you can load it into eCognition and use it together with the other data sets. Last but not least, method fusion. So you can use different methods in eCognition: knowledge-based, unsupervised, computer vision, deep learning, supervised classification. And the cool thing is that you're not bound to one approach, right? You can combine those. So you first of all could run deep learning, right? And based on the results, you could apply knowledge-based classification or unsupervised classification, right? So you can combine those methods within an eCognition project. That's already it. Second part of the agenda is Jonathan's presentation. And a little bit about Jonathan. So he obtained a bachelor's degree in biology in 2012. And Jonathan is free to interrupt me if something is wrong. Since 2013, he's working for the National Park Service in Virginia, specifically in the field of invasive plant management and habitat restoration. And currently, he is a graduate student at the Penn State University. And the focus is on applications of remote sensing data for natural resource management. And I think the presentation today is going to be about his last project. And it's basically about how to identify and assess eastern hemlock trees. Different input data, so four-band imagery, Lidar, and also I think he does change detection. So I'm really looking forward to see what Jonathan has to tell us. So Jonathan, I would give the presenter to you. Yes, so I'm gonna make you presenter. And now you should be able to share your screen.
All right, 1 second.
Yeah, that looks good already. We're getting there.
All right, perfect. Is it? Yeah, okay, I think we're good to go. It's flashing on my end.
Yeah,
right,
now we see. Yeah, we see the PowerPoint presentation, but not the in presentation mode.
Okay, perfect. All right, so thank you for the introduction, Matthias. So today we're going to be taking a look at my capstone project for completion of my master's in GIS from Penn State University. And that was titled A Geographic Object-Based Image Analysis Approach to Eastern Hemlock Management. And before I get started today, I'd like to thank my advisor, Dr. J.B. Sharma, for all the guidance he's provided throughout this entire process. And additionally, I'd like to thank all of my other professors at Penn State over the last 2 years, as each one has played a part in allowing me to complete this project. So with that said, the following is an overview of what I plan to cover today, starting with a brief background on my study topics, specifically eastern hemlock trees and the Hemlock Woolly Adelgid, and then we'll review my research objectives and the methodology, followed by looking at the study area I focused on in the data, and then we'll take a look at the software platforms I used and kind of just the general workflow. A majority of today's time will be spent in eCognition running demos of the rule sets I created to map eastern hemlock trees. And then lastly, we'll look at the results and kind of just reflect on the entire project with some time for Q&A at the end.
Jonathan?
Hi.
Yeah, your slides are cut off at the bottom. I don't know if it's, we do not see the whole slide. I don't know if you can zoom out or.
I can, let's see.
Yeah, I think it's cut off at the bottom and on the right somehow.
Huh. Any better on that end now?
I think it's still cut off at the bottom. So regulate stream temperatures. That's the last line I can read.
Yeah, okay, so that's the very, very bottom. Let's see here.
It's actually the same for the presentation here. It's like it's cut off in the middle of the image on the right.
Oh, here, let me see. Does that look any better now?
I think that looks, yeah, now we see the whole screen.
Yep,
yeah.
That looks better.
Okay, perfect. Yeah, it was just a minor
Awesome. Setting. Yep, perfect. Thank you.
Okay. All right, so let's see here. Once, I want to just get back to where I was. Okay, so my study focused on eastern hemlock trees, which are coniferous tree species meaning they hold leaves year-round in the form of short needles. And under ideal conditions, they can live hundreds of years with tree heights up to 160 feet. And they range throughout the eastern U.S., extending to portions of the upper Midwest, but are primarily found along the Appalachian Mountains. So why would anyone even care about hemlock trees? Well, hemlocks are regarded as a foundational vegetation species within their native range. And what this means is that they influence forest structure in the surrounding ecosystem where they are present, specifically by providing cover and food for animals year-round, including white-tailed deer and various bird species. Additionally, due to their dense foliage, they create constant shade and act as temperature regulators for streams, which is vital for freshwater fish like trout. An example of a healthy stand at hemlocks trees is shown on the right here. And as you can see, it has a relatively open forest floor and is protective against weather events. And so this brings me to the Hemlock Woolly Adelgid, commonly referred to as HWA. It is a non-native invasive insect originating from Asia and was first identified in the 1950s within the eastern U.S. Many reports have cited the first known occurrence happening in Richmond, Virginia, and then spreading shortly afterwards from there. This pest feeds on eastern hemlocks, where it damages the tree and over time leads to defoliation. The damage also restricts water flow within the plant system, commonly leading to mortality. And so the map on the right shows the distribution of HWA. And as you can see, it extends from Georgia all the way north to Maine, kind of reflecting the native range of hemlock trees. The center photo here is a common characteristic of trees affected by this insect, having a white woolly appearance on the branches. This is actually produced by the adelgid while it feeds on the tree, providing a protective insulation layer and a home to lay their eggs in during the winter. The upper right photo shows a typical HWA-affected forest with a dead hemlock tree lying on the forest floor, providing very few benefits for the ecosystem, likely dying over the course of many years from HWA. And so all this fueled my motivation for this project, given the importance of this tree species and the wide-ranging effects HWA would have if it were to fully take out all eastern hemlock trees. My research objectives were split between 2 points. First, I wanted to determine the extent eastern hemlock trees could be identified through geographic object-based image analysis. And then secondly, to determine if I could assess hemlock health over time through vegetation indices, specifically looking at the NDVI and the GNDVI. To do this, I focused my work over 2 regions in Shenandoah National Park, which is in Western Virginia, just west of Washington, D.C., and is a mountainous park, approximately 200,000 acres in size. Of the 2 regions I looked at, we will focus over the primary study area today, being over Skyline Resort, which was chosen due to a large amount of living hemlock trees located there and available data. HWA was discovered in the park in 1988 and has led to substantial decreases in hemlock stand health afterwards. Since then, most of the large pure stands of hemlock trees in the park have been lost to HWA. However, there are remaining populations consisting of singular trees within the forest, and those are the ones I wanted to map in this project. The park has actively managed these trees since the discovery of HWA, starting out with monitoring efforts followed by a shift to control techniques, which consist of a soil application of a chemical to provide hemlock trees resistance against it. And so as a Park Service employee based out of Shenandoah, I've helped with some of the field work for hemlock management there. First-hand experience has shown me there is a need for a rapid assessment and an identification tool for this type of work due to its resource-intensive nature, meaning a lot of hiking is involved during surveys to find these trees, along with person hours to conduct control efforts and health assessments. My thought process was that if I could create automated rule sets to identify trees and assess them, it would be a very useful tool for future management practices. And so once I chose my study areas, I needed data that would allow me to map individual hemlock trees. And this was rooted in high-resolution imagery from the Virginia Geographic Information Network from 2 different time periods, 2009 and 2018. The images held 4 bands, the red, green, blue, and near infrared bands, in 1 foot spatial resolution, being shown here in color infrared. Each collection was taken approximately at the same time, being in late winter during leaf-off conditions. And the leaf-off nature of this imagery was key to mapping hemlock trees in my study areas, as a vast majority of the trees are subdominant species within a multi-story forest, normally having deciduous trees over them. And so in general, my goal with this imagery was to map trees from each time period and then compare them. 2 additional types of data that I used with these efforts included ground truth data, along with making products from Lidar. The ground truth data was in the form of waypoints supplied from the park and represented live managed hemlocks. This information allowed for accuracy assessment and helped when I built identification tables for my knowledge-based classification. The Lidar point cloud was from 2014 and was used to make elevation layers to help with segmentation and object refinement, really acting as a tool to help create initial objects from and also to separate connected tree objects. I created 3 layers in the Lidar, a normalized digital surface model from first return data, essentially defining the terrain and features above ground in my study area. Then I made a normalized digital terrain model from the last returns. And what this layer did was it let me focus on features underneath that topmost canopy surface, being especially useful since most of the hemlocks in my study area were subdominant tree species underneath taller deciduous species, as shown in the picture here. Typically, what I found was that the dominant deciduous trees don't appear in that last return layer, while coniferous species do, since the lower branches are hit by the Lidar pulses, shown by the white areas in the center picture. And then lastly, I made a slope layer from that NDTM to act as an edge layer, which I found useful for discerning between vegetation types and to create initial objects to work with. The software I used was split between ArcGIS Pro and eCognition. In ArcGIS Pro, I pre-processed all my data sets, which included image mosaicing for each time period, and is how I handled the Lidar to create the elevation surfaces. eCognition is where the bulk of the work was done, with image processing occurring through ruleset development. And so this is a general workflow of what I followed in eCognition. I ended up creating 3 rulesets, each in separate projects to keep processing a bit simpler. I began with time period 1, or T1, from 2009, with the goal to map individual hemlock trees from that time period's imagery. The results held 2 classes, either hemlock, which aimed to be only eastern hemlock trees, and then not hemlock, basically holding all other areas. I won't be showing this rule set in the demo today to save a bit of time, but it is very similar to the next one, which we will see. And so the second rule set was almost identical to the first one, but it was just working with the 2018 imagery and having the same final classes. It did need a few parameter and threshold changes, along with correction for some shadow effects in the imagery. This will be the first rule set shown in the demo today. A few definitions to keep in mind as far as classes I used when running the rule set. First, temp and temp2 are used for holding candidate objects, which will be used for that knowledge-based classification at the end of processing, and are objects I want to be as representative as possible to individual trees. The temp3 class was used to hold shadows in the imagery and allowed me to refine those candidate objects. The last rule set, also created as part of the demo, is what I called the change detection or health assessment rule set. And its overall goal is to compare the results from the prior 2 rule sets to see how trees have changed over time. This included creating vegetation indices and tracking those changes as well. So to make more sense of this all, let's just jump into eCognition and see how everything works. All right, so we are we are currently in that time period 2 project for 2018 within the primary study area. And I currently have the 2018 imagery loaded in 4 bands here. Then I also have those Lidar products I was talking about. And so I have that slope layer underneath of the last returns. I also have a digital surface model underneath that. And then I also have just the last return layer, no slope, just the last returns created. And a couple of notes before I really get into the rule set. So this is a very small subset, and not every process I have set up really has a huge effect within it. Some may even throw an error just because the criteria isn't met within the small chip that I'm working in. But I'm going to try to just hit on the major processing steps so you can kind of just see the very big ideas of how I went about mapping these trees in an individual sense. And so with that said, the very beginning of my rule set, it's kind of just split up into 3 sections. First, I'm going to segment the image, building candidate objects, and then I'm going to classify those, and then I'm going to export everything. And so within the first phase of segmentation, I have some very minor pre-processing steps. Delete new level, just a reset button when I run this rule set. The multi-threshold segmentation right here just took care of a small seam line present within the study area. It's not a major thing, so I'm not going to go into it in detail. But really, the project starts out with the second multi-threshold segmentation. And so what I'm doing here is I'm using the multi-threshold segmentation using just that digital surface model to get rid of areas that really have no chance of even holding trees within my study area, just to basically, get rid of areas I don't need so I can focus on just the trees. And so how I have this set up is that, I'm saying anything in unclassified from that digital surface model that is a meter or lower is going to go into a class called low. Everything above a meter tall is going to be kept in unclassified and used to build candidates. And so when I run this, what happens is that I segment the image off that digital surface model underneath, and you can see I start to capture some of the road here in the parking lot. And that's just area that I don't have to really worry about now. It's followed up by using another multi-threshold segmentation, but this time, I'm using the slope layer from that last return Lidar product. And the reason I'm doing that is because when I initially started this project, I tried to segment the imagery, trying to capture these trees. And while some objects were representative of them, a lot of times it was very mixed in, and I was capturing a lot of other, non-target area. And I had kind of an object bleed happening. And it seemed like a lot of work to try to fix all those objects and classify them by using the imagery. And so I started out with the Lidar because it was a lot cleaner of a product. And that last return layer with the slope, it was almost like that slope layer was drawing the trees for me. And so what I could do was use that multi-threshold segmentation and basically say anything unclassified within that slope layer that has a threshold or a pixel value of 40 or higher, I'm going to throw that into that temp class or that first candidate class. Anything under that is going to just stay unclassified. And it'll have a minimum object size of 150 pixels. And so when I execute that, you can see that I'm already kind of halfway there. I have objects that were built off that slope layer that are kind of almost, they're in the neighborhood of where the trees were in the imagery. They don't match up quite perfect, but, I'm already halfway there. And so the next step here, I'm pretty sure this was a very minor step. Didn't have too much of an effect, so I'm not going to dwell on it. But so when I started to look at these candidates, I noticed that, my goal was to map individual trees, and some were connected. And so I wanted to disconnect them to keep them separate. And I did that by using, a watershed segmentation. And so what this does is I'm going to run a watershed segmentation within that domain of the candidate class, so the temp class. And I'm going to use that last return layer here. And when I run the watershed, it's going to look at that last return. I'm using it in an inverted sense. So when the seed object starts within that domain, it's going to start at the brightest pixel instead of the lowest one. And when it builds objects, it's going to grow outwards from that brightest point in the Lidar. And it's going to basically grow until it meets another neighbor. And wherever it meets, it's going to stop. Or it's going to be absorbed if it's under 50 pixels. And so I found that was an extremely useful way to split these trees. And you'll see, you know, they're connected here. Once you run it, it disconnects them basically based off that LiDAR layer underneath. And so, no, they're very minor. I'm pretty sure it didn't have any effect in this study area. And so now my next kind of main processing step was to, you know, take these candidates and start to match them with the imagery, what I call growing the objects into the imagery. And how I did that was I created an NDVI index layer, which I'll use a couple steps later here. Basically, I just wanted some vegetative health in the form of a roster that I could use for objects. So a very simple algorithm to use. Basically, the formula is already there. You just have to line up the image bands for the respective formula. For NDVI, red goes to red, near infrared goes to the near infrared. And when I run this, it's going to create another image layer in my project. That wasn't present. So after that, what I want to do is segment all this unclassified area in between all these candidates, because this is just one giant object right now. And I do that by using two segmentation algorithms kind of in sequence. First, I use the quad tree segmentation with a scale parameter of 40. And once I run this, it cuts up all that unclassified area into little cubes. And then I follow that up with a multi-resolution segmentation that basically looks at all those unclassified cubes. And, you know, I kind of left everything almost at default, except I gave the near-infrared image band a little higher weight because I want to start capturing or give favor to pixels that have a higher reflectance for vegetative areas. And I used a very low scale parameter because I want to make really small image objects. And so when I run that, it's going to resegment all these unclassified areas. And my goal is to get areas that kind of capture the edges of these trees. And so when you look at that, and you can see that it starts to really match up fairly well right next to those candidates. And what I can do after that is essentially throw all these bordering areas that are next to the candidates into their own class by using an assign class algorithm, basically saying that if you are a neighboring unclassified object next to that temp class, so a relative border to temp of greater than 0.01, and you have vegetative health or an NDVI of 0.4 or higher, I'm going to throw you into the temp2 class. So that's going to turn to the yellow here. And then I can attach that portion to my candidates by using the remove objects algorithm. Basically, by in the domain saying that anything in the temp2 class, I want to merge you to the temp class. Basically, how this works is that when you run it, it attaches it to the object with the longest common border that it has. And so at this point, I started to notice that, you know, I'm starting to get the trees a little better, but I still have a lot of area on the back ends that include a lot of non-tree area. And so how I got rid of that was I used the algorithm called the pixel-based object resizing. And this is one of the neatest algorithms because you can basically shrink image objects on a pixel basis under different criteria. So what I did here was I said, well, anything in that candidate class, the temp class, I want to shrink it on a pixel basis in all directions if it has a very low vegetative health or non-existent almost. So anything with an NDVI less than or equal to 0.3. And it's going to run until it basically has no options left. And you can see how it ate away the backsides of these candidate objects, just cleaning up areas where the coniferous tree wasn't. And then I'm going to do the opposite. So you can see there's still some outskirts of the tree that I missed. So I can grow these objects with that same algorithm, just switching the mode. So now I'm going to grow it on a pixel basis within the temp class, basically saying that if you have vegetative health, I want to grow you 5 times. And you'll see how that fills out those areas that I missed kind of the first time around. And so now what I do is, you can see it's kind of just a big mess on the edges, and that doesn't really look like a tree to me. So I want to kind of clean that up. And so now I'm going to use the assign class algorithm to get rid of very small image objects in the temp class that, have an area of 40 pixels or less. And I'm going to put that back into unclassified. And then I'm going to go back through and kind of just clean up very small imperfections, the little holes here that are unclassified within the temp class. I'm going to merge those into that candidate class by using the remove objects algorithm, basically saying if you're unclassified and you have an area of less than 10 pixels, go back into the temp class, and that merges it. And then I want, and I kind of just resplit the trees again using that watershed segmentation from that last return layer within the temp class again. And then I use the morphology algorithms, essentially to smooth the edges of these tree objects. And so I used it 2 different times. The first time I said, well, anything in the temp class, I want to open that image object using a mask. And so the mask that I chose was just a circle mask. And what happens is that it's going to basically run across the temporary class or my candidate class and start to open up the little gaps and kind of smooth the edges a little bit, essentially shrinking the objects. And then I'm going to do the opposite. Using that same algorithm, I'm going to grow those objects just a little bit, just switching the operation here. Same mask. And so when I run that, it'll grow outwards. And it's kind of just making the trees a little more representative, a little nicer looking than what they were. Another minor step. And so now when, at this point I started to look around and I noticed that I was missing some trees in my study area. And so I went through, and this was just cleaning up, merging all those objects again that are unclassified to just kind of have a new starting point. And then I'm going back through and I wanted to see if I could capture these trees that I missed. And so how I did that was I ran a quad tree algorithm, quad tree based segmentation algorithm with a scale parameter of 40. And it's going to cut up that image object into little squares again. And then from there, I basically classified very, very small areas that had vegetative health. So anything that had a 0.4 or higher NDVI value, I'm going to put that into the class called temp2, or my secondary candidate class. From there, I merged all those pixels together with the remove objects algorithm. And then this was just cleaning up very small pixels that were classified in that secondary class or very large pixels. So less than 64 or greater than 1,000 pixels, those weren't trees, and I just was cleaning up my area. And then following that, I'm doing that same edge smoothing routine that I did on the first candidate class. So I'm not going to go into this in too much detail. I'm just going to kind of run it in bulk, but you'll see that it's just going to smooth the edges of the secondary candidate class and kind of fill in a little bit of the unclassified areas. And so at this point, I'm almost happy with my candidate classes. It's almost to the classification point. So I'm just kind of cleaning up my map here. I'm deleting the NDVI layer just to keep my project clean using the delete layer algorithm. And then I'm just basically merging small image objects that are kind of either stuck within a class, either the temp or the temp2 class, just to make them a little more cleaner looking. And so the last phase of this rule set is when I started to look at the green class, or that temporary candidate class, I noticed that I had a lot of shadows included in my tree objects. And this was present throughout the whole study area. And so I wanted to kind of see if I could fix that. And so what I did was I used the multi-resolution segmentation algorithm again, just within that image object domain. So within the temp class, I resegmented just in that area using a very low scale parameter of 20 and giving the near infrared image band a little higher weight. And when I run this, it's going to resegment all these objects again. And I did that so in hopes that I could pick out the shadowed areas and get rid of them, because I didn't really know if it was a tree underneath there. And what I found was that after I did this and I looked at the image objects, I found that all the shadowed areas had a very low near infrared reflectance. And so I used that to my advantage. So I used the assign class algorithm, and I essentially said, if you have a near infrared reflectance of 85 or lower, I'm going to put you into the temp 3 class or the shadow class. And then from that, I can essentially kind of take those away from my objects and get rid of them, so I can really capture these trees well. After that, I'm trying to just clean up the mess I made within that candidate class. So I remerged everything with the remove objects algorithm. And then I resplit them following with the watershed segmentation from that last return layer again. Same process I have been doing, is just kind of like a resetting point for these trees to keep them separated. And then finally, I'm running lastly just kind of another morphology algorithm so I can smooth the edges of these image objects in that temp class. And so when I run this, it's going to use that mask. However it fits it will determine on how the edges actually will appear in the final product. And really at this point, I'm getting to the stage of, I want to start classifying these trees, because I was fairly happy throughout the whole study area with how I was actually mapping them. So when this finishes here, that's where we'll go to next. I'll show you how I went about classification and how I came up with the image characteristics to input into the assign class algorithm. All right, so that smoothed the edges, and these trees are fairly nice looking now, at least for candidates. So I'm pretty sure this was another very minor. Yeah, that's not present here. So now how I went about classifying these trees was, I started looking at image characteristics, but instead of just clicking on one and looking at, one object at a time in the image object window here, I wanted to look at a lot, And when I originally did this project, I had all the ground truth waypoints loaded in from the park. And so I knew what, candidates were really eastern hemlock trees. And so I went through and I selected 100 of these objects that I knew for sure were hemlock trees based off the waypoint vectors that I had in here. And then I used an algorithm called export object stats for report. And what this allows you to do is that you can export object characteristics on a bulk sense for the class you're interested in. And so I basically said, well, anything I have selected within the temp class, which were eastern hemlock trees, I want to export you to a CSV file, and all the characteristics that I chose to look at from those objects I have listed here. And these were all chosen based off, other research that I've read about how others have classified to the species level, either using 4-band data or, other multispectral data from satellites. So I'm not going to go into this in too much detail, but that's just how I populated this list of attributes to export out. And so once you run this, it writes a CSV file. And from that, I opened it in Excel and kind of, looked at the numbers for 100 objects and ran some summary statistics on them just to see what eastern hemlock trees held as far as in this image. And that's how I came up with the thresholds I input into the assign class algorithm for both of those candidate classes. And again, I'm not going to go into too much detail, but that's just how I came up with these values and basically setting this condition for classification for the eastern hemlock tree. And so when I run this, I actually run both of these. It's going to take everything in temp and temp2, and it's going to classify those into the Hemlock class. And so when I run that, you know, the blue and the green areas here are now image objects that I consider hemlock trees based off that ground truth data in the knowledge base classification. And really the last phase here is just to clean up the map and the classes that I have left. So I'm just merging everything with some assigned class algorithms, cleaning up, you know, the multiple classes I have going on. And so what I'm left with when I run this process is a class map with two classes, not hemlock, which is in the white, and then everything in blue here is what I consider a hemlock tree. And at this point, you know, the last phase, I just exported out my results to the vector, which, you know, I'm sure everyone really has experience doing. I use the export vector layer algorithm, and I exported out waypoints and polygons from this class map here. And so really I was done with time period 2. And at this stage in my project, you know, I had the class map from time period 1 done already, or 2019. I have this one done from 2018, but I wanted to compare the results to see how these trees have changed. And so how I did that was I created another project called Change Detection. And I basically created a new rule set to do the change detection. And so what we're looking at here is another very small subset within that primary study area. I have the 2 different image layers loaded in. So I have the image from 2009 loaded in, and I have the one we just looked at from 2018. And then I also have 2 vector layers. So the class map from 2009, and then the class map from 2018. And currently I don't have any image objects. And really the first stage of this rule set, I'm building vegetation indices, because I'm going to use that at the very end to see how these trees have changed based off that vegetation, based off those vegetation indices. And so I specifically looked at the NDVI and the GNDVI. And so to make the NDVI layers for each time period, you know, I use the algorithm called index layer calculation. Very simple to use. You basically just have to make sure you label your image layers correctly. So for 2009, you know, you just match up those layers for the formula. So red from 09 and near up red from 09 go to each layer in that formula for the NDVI. The output's going to be written as NDVI 09. Pretty sure everything else is left at default. And when I run this, it's going to make an image layer for that NDVI index. Same thing for 2018, just changing out the image bands that I used for the formula. And then I made a difference layer from that index. And so essentially I used the layer arithmetics algorithm to make that indice change layer so I can see how the values changed over that 9-year period on a pixel level. And so I took the 2 layers I just created from the NDVI, and I subtracted them from each other in this expression. And I labeled the output as NDVI change from 09 to 18. And so when I run this, it makes a change index layer. And then when I was actually doing this, you know, I exported out all these temporary layers I have in my project to my computer using the export image algorithm. I'm not going to export it today since I already have those as a hard copy. But essentially, you just define the image layer you want to export out, and then you can have it as whatever file format you want. And so for the GNDVI, it was a very similar process, but instead of using the index layer algorithm, I used just the layer arithmetics, solely because it wasn't a predefined option in the other index layer algorithm. And so very simple to use. You just have to make sure you're using the correct image bands. And you write the formula for that vegetation indice. And so the near infrared minus green subtract or divided by the near infrared plus green gives you an output for the GNDVI, which will be output GNDVI 09. And so when I execute this, I get another index layer. Same thing for 2018, just using the correct bands. And then I'm going to do the same thing I did with the NDVI. I'm going to make another change layer so I can see how, those indice values changed over time. And really, at this point, I'm not really too concerned about looking at them today visually. I'm just going to keep them in the back end. And now I want to do that change detection between my class maps, see how these trees have changed over time. And so the first step to do this is to make object or image objects. And I did this change detection by using 3 image object levels in a hierarchy system. So that essentially, I used the vector-based segmentation algorithm to create image objects based off my vector class maps that I produced in the prior 2 rule sets. And so all you need to do is define the thematic layers you want to use to make those objects from. So I said, use the class map polygon from 09 and 18 and create an image object level called level 2 or 2009. And so now we have an object level from 09 with both time periods objects within it. Nothing's classified, but we have image objects for those trees. Now I'm going to make 2 additional levels. And so I'm going to make a level for 2018 below the 2009 level using an algorithm called copy image object level. Essentially saying I want to make a copy of level 2 and put it below 2000, or put it below and call it level 3, 2018. And so now I have that 3rd level, and I want to make a last level, my change level above, which was the same copy image object level algorithm, just taking level 2 and making a copy of it above it, or a super level, and just calling it change level. And so now what I want to do is classify the 2 levels below my change level, because I'm going to use those 2 lower levels for my change detection. And that's very simple to do. So to classify the 2nd level from 2009, I already have all that information in my vector that I have loaded in, or the class map. And so you can use an algorithm to classify image objects based off a vector called assign class by thematic layer. So essentially, you define the level you want to classify. So I want to classify 2009 here based off the class map thematic layer from 09 using the attribute that defines its classification, which was called class name. So when I run that, it classifies that level from that time period. So hemlocks in the blue here, not hemlock in white. And then I'm going to classify that 3rd level for 2018 using the same algorithm again, just a different thematic layer. And so when I run this, I have 2018 classified. And so all that's really left now is to do that change detection I was talking about. And so how I did that is, I want to classify the very top super level based off the 2 levels below it. And I used an algorithm called classification. And how this works is that it'll look at the classes you have set up, and they need to have a class definition defining them. And so the classes I used for that change detection, I had 4 in total. So I had, under the parent class change, I had hemlock decrease and hemlock increase. Within each class, I set up class definitions, essentially making a condition that defines, what makes this class a hemlock decrease. And so when I run that classification algorithm, what's going to happen is that the image objects on that level are going to look below, and it's going to see if this condition is true. And if it is, it'll be classified as hemlock decrease. So essentially, if there is an existence of a sub-object 1 level below the change level when I run that algorithm, and that's true, and then I don't have hemlocks 2 levels below or in 2018, if that condition and both of these are met and they're true, that indicates that it was a hemlock decrease. And so it was the opposite for the next class. So in hemlock increase, in the class definition, how it's defined is You know, if I did not have a hemlock tree in 2009 or one level below the change level, and then I did have a hemlock 2 levels below that change level, if that condition is met, that's considered a hemlock increase. And I will say that there is a very good video on YouTube within the eCognition community of how to set up these definitions for classes. Pretty sure it's the intro to change detection using maps video, and that's kind of how it guided me setting up these definitions. So I won't go into doing that in too much detail today, but that's how I came up with that. And kind of the last major class was the hemlock no change class. Essentially, if there were hemlock objects present in both time periods here, then when I run that classification algorithm, the object will have the class name called hemlock no change. And so once you have your classes set up with class definitions, when you run this algorithm, you just define the level you want to classify. So I want to classify that top level, and then you just choose the classes here that you want to use. So I chose my hemlock decrease, increase, no change, and then not hemlock, no change. And once I run this, what it's going to do is it's going to classify that very top super level based on the 2 levels below and whatever criteria was met. And so what we're looking at here is a change detection map across that 9-year period for hemlock trees. Essentially, the black areas here are objects that were classified in both time periods of hemlock trees, and so it met, the hemlock no change class. The outer rings here would, that's the hemlock increase or indicative of vegetative growth for these individual trees. Essentially, there was not a hemlock tree here in 2009, and then there was in 2018. And then the hemlock decrease class, or the one in red here, is an area that had a hemlock tree or a portion of a tree in 2009, and then in 2018, I did not have an object there, so that was a decrease. And really, at this point, I was almost done with this rule set. Essentially, I'm just exporting out results now. But if you remember, I created all those vegetation indices in the very beginning, and I did that because once I had this change detection map, and I exported out my results, I can export out all those indice values on an object basis because I have all those indices loaded in my project here. And so when I clicked on this object here for hemlock no change, you can see in the image object information window what its indices values were from 2009, so 0.33, from 2018, it increased to 0.49, and then I also have the change here for my change layer, so it increased by a 0.15 value. Same thing for the GNDVI, and I just found it extremely useful for when I exported this out to look at in a GIS, just to see how these indices have changed, over time on an object basis. And so to wrap this rule setup, I'm exporting everything out to points and polygons again. And then lastly, I'm cleaning up this project and getting rid of all these index layers that I don't need anymore. And so rather than clicking save and writing 6 rosters to my hard drive, I'm just deleting everything in bulk using the delete layer algorithm. And so when I run this, it just cleans up all those layers. And I'm kind of back to that starting point again. And so now I'm sure we're all wondering, the accuracy of my classification and, what the health assessment showed over that 9-year period. So we'll look at that next year. All right, so this was my accuracy assessment for 2009 within the primary study area. And I had an overall accuracy of 62.8%. And I had a relatively high producer's accuracy for the hemlock class, but a very low user's accuracy. And what that really told me was that I captured a large amount of hemlock trees within that study area, but I also captured a lot of other tree species that were coniferous as well. So I had species confusion going on. And I had similar results in 2018. When you look at the accuracy assessment for that time period, I had an overall accuracy of 58.8%. Like 2009, I classified a large amount of hemlock trees, but I also captured a lot of other non-target tree species, which was reflected in the user's accuracy of 22% for the hemlock class. And just the final class map here, the black areas are very small objects that I classified as hemlock trees. And while some of them were actually hemlock trees, there were just a lot of other tree species I started to capture as well. And I just made an overlay raster here that kind of showed the concentrations where I classified more objects than others within that hemlock class. And so the health assessment. So how I went about doing this was, rather than look at all the objects that were called hemlock tree and do assessment on trees that some that weren't really hemlock trees, what I did was, in a GIS, I took a subset of my results. So any hemlock object that overlapped with a ground truth waypoint that I knew was an actual eastern hemlock tree, I just looked at those. And then from that subset, I took an average indice value for the NDVI and the GNDVI. And I found that, for all the eastern hemlocks that I was able to map, the NDVI increased by 41% over that 9-year period. And then it was similar in the GNDVI, it increased by 39%. Kind of suggesting that the hemlock tree health is increasing, likely due to management practices from the park, actively managing these trees against HWA. And so just a reflection on everything today, overall this project, I felt that I produced a very robust mapping tool for individual coniferous trees. I felt that the health assessment worked very well. Essentially it worked well since I was able to map the trees so well through eCognition, and then also the ground truth data allowed me to look at actual hemlock trees. And then in the full project scheme, I actually had a very small secondary study area where I took that time period 2 rule set we saw today for 2018, and I used it in a brand new area just to see how it would actually map trees again. And what I found was that it exhibited good rule set transferability. And the overall accuracy for mapping hemlock trees actually increased to 73% in that much smaller area, likely due to being smaller compared to the primary study area, and also really just being dominated by hemlock trees there. And as far as future work for this project, I'd like to take it and start incorporating additional sensors, either satellite or UAVs, to enhance spectral and spatial information to hopefully improve classification results. I would be curious to see how machine learning classifiers would do, either with this data classifying these trees, or using additional information and then going that route as far as my classification. And then in the long run, I would like to use these rule sets with the eCognition server to essentially map the whole 200,000 acre park for these trees, in a bulk sense, in a timely manner with the server. So yeah, I'd just like to say thank you for having me today, and that's just about everything I have as far as my presentation goes. So I'll hand it back to you, Matthias.
All right, thank you, Jonathan. Very interesting, very nice presentation, very nice demo actually. You really explained the rule set in detail, and I really liked it. Especially for me, I must say at the beginning how you rework those image objects, right? Because usually a lot of users expect to have perfect objects after segmentation, but those are more or less like really the building blocks, right? And then you can work on them, pixel-based object resizing, merging, then removing objects. So I really like that.
Thank you.
I'm quickly going to switch back to my slides. I hope you see my slide here. So Q&A. Michael, maybe you can throw some questions at Jonathan.
Sure. We're getting a lot of really good feedback. Thank you very much, Jonathan, for your great presentation. We are running, I think, past the time, but it would be nice if we can answer a couple of quick questions. Jonathan, is that okay for you?
Yeah, no, that's fine.
Okay, great. Thank you for the presentation. Did you explore perhaps supervised classification, random forest, or SEM as an alternative to the knowledge-based approach using the statistics export?
You know, I haven't. I did not try that route, but those are kind of steps I'd like to try as far as additional work, just to see how the classification would either improve or just compare to what I did. But yeah, no, I haven't tried that yet.
Maybe a follow-up for maybe Matthias can also chime in here. What would be the pros and cons for a supervised approach versus a knowledge-based approach? The one we've seen here.
As far as pros and cons, I mean, I guess the cons would be that, I guess I felt like I had more control, or, I could put more of just my knowledge into the threshold values I used for the classifications, as opposed to doing, well, I guess supervised, you could still control it as well. Honestly, until I could actually run supervised classification, comparing it against this knowledge-based routine I did, I couldn't really truly say, for sure what the pros and cons would be. I would just be interested to see how the results would compare to each other in that sense.
Yeah. I mean, Jonathan, you're 100% right. Supervised classification, you do not have 100% control, right? But you easily could ingest that now into your rule set, right? Replace the classification part with the supervised classification, and then see how the results look like, right?
Yeah, no, I mean, it would definitely be interesting. The next steps, I would like to just try different classification methods to see, which would work best in the long run for hemlock trees. But.
Thank you for your answer. Our next question. Thank you for the valuable lessons about tree mapping. Did you have any issues with different image states within your study area or year? And did that affect your object statistics? If so, how did you address that?
Well, yeah, so that's funny that I was asked, because I did. So the imagery wasn't perfect. When I looked at the whole study area I worked in, especially with the high relief within the area, it was a very mountainous region. So there were, image blurs and shadows and, seam lines that weren't perfect. And so those were areas that when I ran, creating candidate objects and classifying, I was picking up on some of these error areas, and I think that contributed to some of my results. And how I kind of tackled that was, I tried to get rid of those areas as much as possible. For example, if I had hundreds of little candidate objects where there was an image blur, I tried to tease those out and get rid of them in my candidate class by using different size characteristics, or different relationships that basically would identify them as errors, to mitigate that as much as possible.
Thank you for your insight. Our next question. Hi, is there any table criteria that summarizes the best algorithm according to the targets, such as terrain or vegetation? Or do I have to decide by comparing each algorithm one by one? I would like to know more about the method or criteria for selecting algorithms.
I mean, as far as selecting the algorithms, I mean, I didn't have a table per se. I mean, a lot of my selection choices were either based off, other work that I read as far as mapping tree canopy went, and then also, just watching, other webinars and other help videos of what other folks have done. And, that kind of guided my really trial and error process as far as using different algorithms to map these trees. I will say, I mean, it took me a very long time in the beginning, kind of using different algorithms in a different sequence, it probably took a few weeks just to really find a good flow in the rule set as far as mapping these trees. So it was really a trial error approach, and that's how I kind of went about that.
Yeah, for sure, there's a bit of a subject expertness to using finding the right algorithms, and you can always check the documentation and check our YouTube channel for tutorials, and I usually get good feedback on that's a good starting place for these things. No. But next, how did you do the accuracy assessment? Did you go to the field to count the hemlock trees, or did you do a visual interpretation?
Well, so how I did the accuracy assessment, so I had, from Shenandoah National Park, they take waypoints in the field with GPS units when they go and manage these trees. So I had all the ground truth waypoints that were collected by other people. And so how I went about doing the assessment was, I used those waypoints as my ground truth, kind of my verification points. And wherever they overlapped with an object, I knew that was a hemlock tree. Essentially, I think I had, probably 4,000 waypoints within the primary study area as far as actual true hemlock waypoints. And then I just used that as input for my, visual identification in a GIS as far as doing the accuracy assessment.
Good. We're having some more general questions. Is there any algorithm of DL with Obaya in eCognition?
Can you repeat that question again? Sorry.
Is there any algorithm of deep learning with Obaya in eCognition?
There is.
Yeah.
Yeah, I think that we can answer it.
I was just going to say, I know there is, or I'm pretty sure there is. I haven't personally used it for deep learning, but Matthias.
We have several deep learning algorithms. So you can create sample patches in eCognition, create a model, train a model, and apply a deep learning model. But you also can load external models, right, and apply them in eCognition. And we have also several videos on YouTube, I guess 2 or 3 on this topic, and also a free tutorial online. But I'm going to show you some links afterwards. Right.
Okay, and we have one more simple question. What is the slope NDTM? What is the difference with a typical DEM?
So the slope DTM, so the DTM I used, it was a digital terrain model, but instead of using, the ground returns to make just a bare earth surface, what I used was the last return layer, or the last return points from the Lidar. So essentially, some of those points were probably ground, but other points were actually hitting kind of mid-height 3D objects. And I did that because typically coniferous species, specifically the hemlock tree, has lower branches that would be picked up from that pulse return. And so it was kind of making a slope layer from those last returns essentially made an edge layer that I could use to make those initial candidate objects from in the very beginning of my rule set.
Mike, maybe one more question, and then I'm gonna wrap it up.
Question: Is it would be used to detect landforms, for example, terrace or landslides? Could this be? I guess the question is, could this be used to detect landforms, for example, terrace or landslides? Yeah.
Oh, definitely. You could use this methodology to detect, not only trees, but, rock outcroppings, landforms, a major disturbance within the forest. If you made a DEM surface and, took a hill shade of that and used that as an input, you could use a segmentation algorithm to capture, that disturbance area, say a landslide, and then map that out, and go from there as far as what you're looking at. But
Okay.
I think we'll wrap up questions. If you have any questions regarding buying eCognition or your local dealer, just send us support a message. Go to eCognition.com. And we couldn't get to all the questions. Sorry about this. But if you have any questions, always contact us as support, or you can leave a message on our community. Back to you, Matthias.
Thank you, Mike. We're gonna reply to all your questions that you've asked here, right? So no worries about that. And so this webinar is recorded and it's gonna be uploaded to our YouTube channel. So no worries, you can rewatch it. And there's also video on landslide detection, a webinar that we did last year. So for the resources, if you go to eCognition.com, you're gonna find all the links to our knowledge base and community, to the social media that we have, training material. So we have a lot of free training material right online to support. We have a blog, documentation, the webinars, and eCognition TV. That's our YouTube channel. So if you go to eCognition.com, you're going to find all these resources there. You also can use these QR codes. They're going to get you directly to those websites. And finally, to get inspired, right? That's some videos from our YouTube channel, webinars, tutorials, specific videos on specific algorithms, right? And you can use the free trial version if you want to play around and test it. So you don't have to pay anything. And a lot of the training material is also for free. So I think that's it. Thank you very much, Jonathan. I really enjoyed your presentation. If you have questions, right, contact me or Jonathan regarding this webinar. And again, it's going to be uploaded next week. And thank you all for participation and all the questions. And have a good rest of the week and goodbye.